Hello everyone, and thanks to the organizers for giving me a chance to present this topic of photochemical properties and applications of azobenzene modified polyurea systems. I am Sreeram Kalpathy from the Department of Metallurgical and Materials Engineering at IIT Madras. And this talk is based on the work done by my PhD student Swati at IIT Madras. I'll be following this outline. I will first give an overview of the concept of photoresponsive polymers, followed by some details on synthesis and characterization of azopolyurea, the specific polymer which my student has worked on. I will be discussing the photochemical response of this polymer and the illustration of its use in light-assisted patterning. And the last part of my talk will be on blends of azopolyurea and polystyrene and how we manage to get some visible light response from it, followed by some conclusions. Now, controlling molecular alignment by light is a very useful and facile way of modulating properties and functionalities of materials, especially polymers, because you can incorporate photosensitive functional groups into polymer chains. And in this way, one can change several aspects of the chemical structure of the polymer, such as conformation, polarity, charge, conjugation, etc. And these in turn can cause changes in the physical properties of the polymer, like shape, as in shape memory polymers, phase, wettability, and solubility characteristics. Now, there are several advantages to using light as a stimulus for structure property manipulation. First is that it is a non-destructive method, unlike, say, chemical or thermal or mechanical stimulus. Secondly, and this is particularly useful, is that many photoresponsive effects are reversible changes. That is, a change in structure brought about by one wavelength of light can be reversed often by another wavelength of light, because these changes are based on electronic band transitions or excitations by absorbing or emitting energy. Then thirdly, light is something that can be triggered from outside the system without physically contacting the molecules or disturbing their surrounding environment. And of course, light can be switched on and off fast, quick switching and easy focusability, which, unlike in the case of chemical energy, where it is harder to control the location and concentration of the reagents, with light, one can easily control the wavelength, focus, location, and the intensity of the light source. And of course, elimination of chemical reagents and waste byproducts is an added advantage. So in this work, we have been working on an azobenzene containing polymer, which azobenzene is a molecule, an organic molecule that has cis and trans isomers. The trans isomer, when exposed to UV light, converts to cis isomer and back to trans upon shining visible light over it. Trans azobenzene is flat. It has almost no dipole moment, whereas the cis presents an angular geometry with dipole moment of about 3 dpi. So isomerization in azobenzene is not the only type of photochemical response that we get to see. There are other examples in other types of molecules like triphenyl methane derivatives where ionic dissociation occurs, or cinemates or polystyrene where photoreactions like cleavage of bonds or cross-linking can occur. We have incorporated azobenzene group into polyurea, and hereafter I'll be calling this polymer as azoPU. Now, one way to incorporate azobenzene moieties into a polymer is by doping the chromophore into the matrix of the polymer. But because of the high mobility of these units, a polymer film doped with azobenzene would exhibit instabilities such as phase separation. And the dipolar azo units are also prone to aggregation, leading to microcrystallization. A better way is to covalently attach the azobenzene into the main chain of the polymer, which gives greater stability and control. So my student has synthesized azo-PU by polyaddition reactions between toluene diisocyanate and diaminoazobenzene in NMP solvent in nitrogen atmosphere. The polymer was produced as a solid paste, which was precipitated and dried into powder form, then dissolved in DMF solvent and spun coat at 2000 RPM into a thin film of a film thickness of 200 nanometers. So attaching azo group covalently to the main chain gave the polymer a high TG and thermal stability. And it also offers delayed kinetics of the reverse cis to trans isomerization, which is useful in case you want to retain the cis isomer intact for a longer duration. So this is the DSC and TGA spectra of azopolyurea. There are clearly two distinct transitions at 163 and 333 Celsius. And these can be attributed respectively to the glass transition and melting. And this is also consistent with the TGA observations, which show steps around 160 and 330 degrees Celsius. The weight loss at 330 is due to the exothermic decomposition of the N double bond N in the polyurea backbone. So this is an optical micrograph of azo-PU showing birefringence, suggesting some kind of molecular ordering or semi-crystallinity. And this is the X-ray diffractogram of azo-PU, in which these peaks correspond to these interplanar spacings, and a couple of which arise from hydrogen bonding. So all these reasons strongly suggest that azo-PU is a semi-crystalline polymer, and this is a possible schematic of how hydrogen bonding can exist between the C double bond O and the NH groups of neighboring azo-PU chains. In fact, in the cis isomer, it can also exist in an intramolecular fashion. And given that there are abundant aromatic rings in the backbone, it's quite likely that the chain is very rigid and leading to its semi-crystalline nature. Now we expose this thin film of azo-PU to an intense beam of 365 nanometers using bandpass filters in a xenon arc lamp. And here is the UV visible absorbance spectra, which of the film before and after UV exposure. So we see here that there is a strong absorption in the UV region corresponding to the pi to pi star transition of azobenzene. There's also a weaker band in the visible region, which corresponds to what's called the N to pi star transition in azobenzene. And this is the typical absorbance spectra of cis and trans azobenzene molecules. So the decrease in intensity of the pi to pi star and the relative increase in the N to pi star intensities after UV exposure is actually signature of the trans to cis isomerization after UV exposure. And this was also confirmed through contact angle measurements. The contact angle of the trans azo-PU is expected to be higher due to its smaller, lower surface tension, given that it doesn't have a dipole moment. Whereas the contact angle of the cis azobenzene is slightly lesser due to its higher surface tension. And we are able to recover the contact angle upon visible light exposure, suggesting that the reverse isomerization occurs at visible light exposure. Now, we have used this azo-PU to illustrate light-assisted patterning by the mechanism called self-organization. A thin film, polymer film spin-coated at high RPM is thermodynamically unstable. When heated above its glass transition temperature, any roughness or perturbations on the surface of the film would amplify and would reorganize the film into other metastable conformations, which could be, for example, a random array of dewetted droplets. And we can take advantage of the photochemical nature of SOPU to make reversible patterns and versatile patterns of various feature sizes by selective light exposure using masks. So here is a typical experiment. A spin-coated film is exposed to light through a mask that transmits UV light selectively, which locally converts the thermodynamically stable trans state into the less stable cis state. Now, when this film is heated above its TG, the fluidic polymer flows from the masked region to the exposed regions due to the presence of surface tension differences between the cis and the trans isomers. And this kind of flow is called Marangoni flow. And combined with other local hydrodynamic flow mechanisms, we end up with some kind of ordered features like these. We see cylindrical shaped pillars of about 800 nanometer height and separated by about 75 microns. Each of these is about 25 micron wide. And you could also do that with the backward reaction. That is, if you start with an all cis structure and uniformly expose it to UV light, and then selectively exposed to visible light to cause depressions or holes in the exposed regions. And of course, Marangoni flow is not the only flow contribution. There are other flow contributions like viscosity gradient driven flow and mass migration that can happen at smaller length scales. So this is how one such pillar looks like. It's a circular dome shaped morphology. And with the backward reaction, you get an array of holes and pillars which are ordered and uniformly distributed. We can also produce interconnected structures like these by using photo masks of smaller separation. What I showed you previously were features with masks of exposure width of 5 millimeter, whereas with exposure widths of about 10 micrometer, you can restrict the local hydrodynamic flows and the pillar separations can be made closer to the mask feature sizes. And because of restricting local hydrodynamic flows, you get these elevations and depressions interconnected by threads of fluidic polymer. We have tried to use these patterns for protein adsorption. Now, many proteins adsorb preferentially over hydrophilic areas with greater interaction strength than hydrophobic surfaces. SOPU being a relatively hydrophilic polymer, and given that hydrogen bonding interactions between polyurea and the proteins would favor adsorption, we explored the adsorption of bovine serum albumin on these patterns. This is the optical profilometric image of the patterns before adsorption. And these larger spots are the top of the pillars onto which these proteins have absorbed. And these are the proteins. And here is a confocal micrograph of that showing fluorescent regions when the protein had an FITC label. Now, considering the problems associated with UV responsive polymers like photooxidation and its non-suitability for biomedical applications, we have tried to design a visible light responsive polymer blend by blending SOPU and polystyrene in DMF. So here is the UV visible absorbance spectra of SOPU on the top and PU-PS blend at the bottom. What we see here is that the two signature peaks of SOPU appear as a single broad peak ranging from about 300 nanometer to 560 nanometers. The pi to pi star and the n to pi star bands overlap, and there's an overall red shift of the absorption peak from 343 to 360 nanometer. And here are the spectra for various compositions of SOPU and polystyrene in different volume percent. There is definitely more prominent broadening and overlapping of peaks for higher polystyrene volume percent. We've also done exposure studies to confirm that trans to cis isomerization is brought about, and therefore it shows tangible response to visible light. The proposed mechanism for redshift in the overall spectrum is that the polystyrene invades the ordered lattice of SOPU and disrupts the hydrogen bonding, confirmed by the absence of the relevant peaks in the X-ray diffraction of the blend and the pure polymer. So this implies that the trans to cis conversion can take place with lesser input energy. So it can be caused by visible light instead of UV light. With that, I will conclude with conclusions that photoresponsive azo polyurea synthesized has high TG due to the covalent bonding of azo group in the backbone of the polyurea chain. Self-organization and Marangoni flow lead to ordered patterns in azo-PU, which serve as templates for protein patterning. And finally, blending azo-PU with polystyrene causes redshift and transition overlap of the UV visible absorption spectrum. I would like to acknowledge the grant and the various labs from whom we have taken help to do these experiments. And thank you once again for your attention.